11.2 Analysis Model. Non-isolated system angular momentum. The outline of this video is as follows. We will start with a conceptual introduction to angular momentum, exploring why it is the rotational analog to linear momentum. Next, we will develop a precise mathematical definition for the angular momentum of a single particle. We will then expand this idea to describe the total angular momentum for a system of multiple particles. Finally, we will see how to apply these concepts using a formal analysis model and by working through several examples. We are now going to explore angular momentum, a crucial concept for analyzing any kind of rotational motion. You will recall from our study of translational motion that linear momentum is a measure of an object's motion in a straight line, and that a net force is required to change it. Angular momentum is the direct rotational analog to linear momentum. It provides a way to quantify the rotational motion of an object or a system of objects. Just as a net force causes a change in linear momentum, a net torque is what causes a change in angular momentum. To build our intuition, consider the example of an ice skater gliding past a pole. When she grabs the pole, her motion instantly changes from linear to circular. This change is precisely what the physics of angular momentum helps us analyze. So the key idea is that angular momentum is for rotation, what linear momentum is for translation. We can derive the rotational version of Newton's second law by starting with the linear form. This derivation will reveal a new and important quantity for describing rotational motion. We begin with the familiar statement that the net force on a particle equals the time rate of change of its linear momentum. Next, we take the cross product of both sides of this equation with the position vector, r. The left side of the equation, r cross net force, is simply the definition of the net torque acting on the particles. Now let us analyze a separate but related expression, the time derivative of the quantity r cross p. Applying the product rule for derivatives gives us two terms. The first term is the time derivative of r crossed with p. Since the derivative of position is velocity, v, and momentum is mass times velocity, this term is v cross m times v. Because the velocity vector is always parallel to the momentum vector, their cross product is 0, and this first term vanishes. This leaves a crucial result. The net torque on a particle is equal to the time derivative of the quantity r cross p. This strongly suggests that the quantity r cross p is the rotational analog of linear momentum. We can now introduce the rotational analog of linear momentum, a crucial concept called angular momentum. Our previous derivation showed that the net torque on a particle equals the time rate of change of the quantity r cross p. This structure is a perfect parallel to Newton's second law, where the net force equals the time rate of change of linear momentum, p. Because of this powerful analogy, we formally define the quantity r cross p as the instantaneous angular momentum of the particle, which we represent with the vector L. So angular momentum L is defined as the cross product of the position vector r and the linear momentum vector p. As the figure shows, because angular momentum is a cross product, it is a vector. Its direction is perpendicular to the plane containing the position and linear momentum vectors, determined by the right-hand rule. This definition allows us to state that the net torque on a particle is equal to the rate of change of its angular momentum. The definition of angular momentum as a cross product gives us a powerful rotational version of Newton's second law and specific rules for its direction and magnitude. First, just as force is the rate of change of linear momentum, torque is the rate of change of angular momentum. The equation torque equals dl dt tells us that an external torque is required to change a system's angular momentum. The direction of angular momentum is always perpendicular to the plane formed by the position vector r and the linear momentum vector p, as determined by the right-hand rule. The magnitude is L equals mv r sine phi, where phi is the angle between the r and p vectors. This leads to a crucial insight. An object does not have to be rotating to have angular momentum. For instance, A particle moving in a straight line has angular momentum about any axis not located on its direct path. The key takeaway is that angular momentum depends on the object's motion relative to a chosen origin. Let us apply our definition of angular momentum to the important case of a particle in uniform circular motion. A common pitfall is to assume that because the particle's velocity vector is constantly changing direction, its angular momentum must also be changing. However, we will see that this is not true. Consider a particle of mass, m, moving at a constant speed, v, in a circle of radius r. At any point, the position vector r, drawn from the center to the particle, is always perpendicular to the linear momentum vector p. This means the angle phi between them is a constant 90 degrees. The magnitude of the angular momentum is L equals m times v times r times the sine of phi. Since the sine of 90 degrees is exactly 1, the magnitude is simply L equals mv r. Because the mass, speed, and radius are all constant, the magnitude of the angular momentum is also constant. The direction of the vector L, found using the right-hand rule, also remains constant, pointing along the axis of rotation. Therefore, a particle in uniform circular motion has a constant angular momentum. Now we will extend the concept of angular momentum from a single particle to an entire system of particles. The total angular momentum of the system is, quite simply, the vector sum of the angular momenta of all the individual particles. The time rate of change of this total angular momentum is therefore equal to the sum of all torques acting on every particle in the system. This is where a powerful simplification occurs. The total torque comes from both external forces and internal forces between particles. However, because of Newton's third law, internal forces always occur in equal and opposite pairs. If these forces act along the line connecting the two particles, their torques about any point are also equal and opposite. When we sum up all the torques across the entire system, every internal torque is perfectly cancelled by another. Therefore, the net torque from all internal forces is zero, which is a crucial insight for analyzing the system's rotation. We can now state the central principle for a non-isolated system in rotation. A net external torque must act on a system to change its total angular momentum. This is the core of the non-isolated system model for angular momentum. The governing equation is that the sum of the external torques equals the time rate of change of the total angular momentum vector, L tot. This relationship is the direct rotational analog of Newton's second law for a system, which equates net external force to the rate of change of total linear momentum. If we integrate this rotational equation over time, we get the angular impulse angular momentum theorem. It states that the total change in angular momentum, delta L tot, equals the angular impulse, which is the integral of the net external torque over time. For instance, applying a torque with a wrench for a few seconds delivers an angular impulse that changes the angular momentum of a bolt. The key takeaway is that net external torques are the cause of changes in angular momentum. Let us now apply our non-isolated system model for angular momentum to solve a familiar type of problem involving a pulley. The physical setup consists of a sphere of mass m1 and a block of mass m2, connected by a cord that passes over a pulley with rim mass m and radius r. The block rests on a frictionless surface. Our goal is to find the linear acceleration, a, of the block and sphere after the system is released. To do this, we will treat all three objects, the sphere, the block, and the pulley, as a single system. This is a non-isolated system because there is a net external torque acting on it. The source of this external torque is the gravitational force on the hanging sphere. We will calculate both the torque and the system's total angular momentum relative to the pulley's axle. By relating this net external torque to the rate of change of the total angular momentum, we can derive an expression for the acceleration. We will now solve for the system's acceleration by applying our model for a non-isolated system. This means we will set the net external torque equal to the time rate of change of the total angular momentums. First, we calculate the total angular momentum, L, of the system about the pulley's axle. The sphere, the block, and the pulley rim all share a common speed, v. By summing the individual angular momenta of each part, we find that L equals the quantity m1 plus m2 plus capital M, all multiplied by v times r. Next, we identify the net external torque. The only force producing a torque about the axle is the gravitational force on the hanging sphere, m1 times g. This gives a net external torque of m1gr. We then set this torque equal to the time derivative of the angular momentum. Since the masses and radius are constant, the derivative of speed, v, with respect to time, is simply the linear acceleration, a. Solving the final expression gives the acceleration as the driving force, m1g, divided by the total mass of the system that is being accelerated. Let us take a moment to summarize the key definitions and principles we have established for angular momentum. We started by defining the angular momentum of a single particle, L, as the cross product of its position vector r and its linear momentum p. From this definition, we derived the rotational analog of Newton's second law, which states that the net torque on a particle equals the time rate of change of its angular momentum. We then extended this principle to a system of multiple particles. The crucial insight is that the torques from internal forces within the system cancel out in pairs. This simplifies the situation immensely, leaving only the external influences. Therefore, for an entire system, the net external torque is what determines the change in the total angular momentum. This relationship is the foundation of the non-isolated system model for angular momentum, which we use to analyze how the rotational motion of a system changes in response to its environment. Let us use these two questions to review our understanding of angular momentum. The first question asks about a particle moving in a straight line with constant velocity. To determine when its angular momentum is constant, let us think about the definition. The magnitude of angular momentum depends on the particle's mass, its speed, and the perpendicular distance from our chosen origin to its line of motion. Since mass and velocity are constant, the key is that perpendicular distance. For any straight line path, this distance is also constant. Now, for the angular momentum to be zero, that perpendicular distance must be zero, which only happens if the line of motion passes directly through the origins. The second question compares the angular momentum of a solid sphere and a hollow sphere. For a rotating rigid body, angular momentum equals the moment of inertia, I, times the angular velocity, omega. The problem states that the mass, radius, and angular velocity are the same for both spheres. This means the object with the greater moment of inertia will have the greater angular momentum. So which one has a greater moment of inertia? The solid sphere with its mass distributed throughout, or the hollow sphere where all its mass is concentrated at the maximum radius?